everyone. This is the second lecture of the mathematical module of the mini course on computation. And today we're going to talk about more modern developments on like different computational models, computational resource, and something called reductions. Yeah, but before that, maybe very quick two reminders on the logistics sides. Yeah, so the first is about signing up for Scribe Notes. So the idea of Scribe Note is maybe a US culture. Yeah, like people taking the same course, taking like collaborative notes together. So this will like help each other's learning together and also recall what happened in the lectures that's just spoken out by the lecturers without written on the slides. Yeah, so it's very lightweight, and we will also help you polish it. So it will, I promise you, it will be a very rewarding experience. Yeah, and the second thing is this is a visualization of the mini course schedule. In case people don't know, you actually can click this different tab on the course website, so you can see the like the geometry of the course better. Yeah, to have a sense when each lecture starts. Okay, so hope this work, and also hope everyone are here now, so we can formally start the lecture. Yes. So yesterday, during the first lecture in module 1, we talked about some mathematical formulation of computation. Yeah, trying to see, okay, now we have some vague intuition about computation, but what if we want to study from mathematical, formal, rigorous way, how to do it? Yeah, and we see like Hilbert as this Hilbert's dreams problem. Yeah, and in the end, we see how like a Turing formulate the intuitive idea of Turing machine that capture mechanical procedure and use it to refute Hilbert's dream. Yeah, and we also discussed a little bit about like a Turing machine as mechanical procedure actually is kind of like a assumption or hypothesis, and we call this Church-Turing thesis, and this will be discussed more in the third lecture. But now let's go back to today. In this lecture, we are going to focus more on some modern developments. So I'll give you a very quick overview on like what's happened in this field called theoretical computer science. Yeah, to let you know roughly like what people in this area is doing, and what's like there are some big items there in the big picture. Okay, so the first part I'm going to talk about is about like different computational models. So yesterday we mainly only focused on Turing machine, but actually Turing machine is not alone. There are lots of different computational models, including some weaker model, in the sense that they are mathematically weaker than, sorry. Yeah, sorry about that. Yeah, in the sense that those weaker models are mathematically weaker than Turing machine. So that actually there are some problems, computational problems, Turing machine can solve, but a weaker model cannot solve. And maybe some textbook example is finite automata. But one thing I like even better is something called regular expression. So for those who actually do some real coding, you will actually know regular expression quite useful for you to find like certain patterns in like a text. Yeah, but this is actually weaker than Turing machine. Yeah. In the meantime, there's also lots of Turing complete models, which already kind of been asked in yesterday's questions. Yeah, like there are other computational models or even logical system like lambda calculus. Mathematically, they are equivalent to Turing machine in the sense that whatever Turing machine can do, they can do. Whatever they can do, Turing machine can do. Yeah, so this includes like lambda calculus, and this will be slightly elaborate in our advanced section this afternoon by Rayon, and also including programming language. Basically all the programming language are Turing complete, and even some video games are Turing complete in some sense. Yeah. And finally, there are also some other models that are not exactly compute things in a similar way, but also mathematically rich and well studied, including circuits. and communication models, which we will elaborate in the next few slides. But here I just want to give you an overview that like there are indeed lots of computational models. So let's start with, so let's start with circuits. Yeah, so when it comes to circuits, maybe what people come into mind is electrical circuits you learn in high school, or like for double E people, you see this integrated circuits. But this is not what we are going to talk about today. Yeah, today we focus on the mathematical abstraction of circuits. Yeah, so in mathematics, circuit is modeled as like you have like two ingredients. One is gates and one is wires. So gates is like something computing some local computations. For example, in the first example is a Boolean circuit. We are computing a Boolean function, meaning that everything is 0 and 1. Yeah, so the gate now is a logical AND or logical OR. And there are also wires, yeah, like connected those gates in a directed way. Yeah, and this forms like a circuit, and they are computing certain functions. Yeah, and Boolean circuit is not alone. You can also replace the gates into other computational units. For example, you can do like addition multiplications, and this becomes like arithmetic circuits. And you can also replace gates to be something called quantum gates, yeah, which we will mention maybe in the second module on the physics part. Yeah, and then this becomes a quantum circuit. Okay. And but before I give you an example on what does the circuits really compute, maybe one thing you might already notice, and maybe for those who see this before, you know that the main difference between circuits and Turing machine, and the reason why I put in the other computational model category is like because the number of inputs in the circuit is fixed. Unlike Turing machine, you can handle all possible inputs. Yeah, the input, like the circuit size is fixed when you fix the circuit. Okay, now, so I just give you like animations on like how circuits do computations. Yeah, so for example, on the left, the Boolean circuits, if you give it some input, meaning that setting some variables to certain value, basically what you did is just like doing the direct replacement of the value. So you replace the input variable to this, and then evaluate each local unit, and then you compute and get the result 0. So the Boolean circuits indeed is compute a Boolean function. And similarly, in the arithmetic circuits, it is basically computing something called a multivariate polynomials. And feeding on certain inputs here, you can get something like 17. Okay, so hope this already gives you a feeling that, oh, circuits is also quite a reasonable computational model. And it is also different from Turing machine in the sense that the input size is fixed. Okay. And the second example I want to introduce maybe is slightly common for people outside theoretical CS, but I want to show you because this is quite interesting and actually quite deep and illuminating. This is called computational communication models. So in this model, the easiest, simplest setting is where you have maybe two persons. Usually we call it Alice and Bob. Yeah, and basically you can think of them mathematically as like a two-to machine. Yeah, and they are separate from each other. They can communicate with each other. And unlike the Turing machine is computing a function with single input, yeah, here we think of both of them are together collaboratively compute a function with two input. This is like the first part of the input. This is the second part of the input. Yeah, and Alice will receive input X, Bob receive input Y, and the goal is to compute f of X, Y through like many communications. Yeah, so you can always see the simplest way to do it is just like, oh, Alice send the whole X, yeah, to Bob, and Bob can compute f because Bob has like a Turing machine is very powerful. It can directly compute f. So it is really about like one side don't know the input of the other side, but if you don't know it, can you still efficiently compute it? Okay, so similarly, I'll give you a simple example to have a feeling on like what this model is really about. And this is a very simple example of something called equality. Yeah. So think of now like Alice, yeah, have like 5 bits of input, yeah, say 0, 1, 0, 0, 1. And Bob also have 5 bits of input, say, for example, 0, 1, 0, 1, 1. Yeah, and this equality function, the goal is to see whether Alice and Bob, their input are the same. Yeah, so maybe take a moment also at the mathematical description to make sure you understand the function. Yeah, so you can see that in this setting, indeed, the trivial way to do that is Alice sends all the bits to Bob, and Bob can check whether the input of Alice are sent to him. Yeah, but the question now becomes like, oh, can you do much better than that? Can you use less than 5 bits of communication to do that? Yeah, and it turns out that one like a fundamental result and quite influential result, interesting result here is that it turns out that 5 bits is needed. Yeah, it turns out that if you use this kind of way to collaboratively check whether Alice and Bob have the same inputs, you indeed need 5 bits of information, regardless like what kind of information you are sending to each other. So the proof is a little bit involved, but intuitive way to think that is like, for example, when they fix a way to say, oh, the first time I'll send the first bit and second, third, and last, you can always find certain input, yeah, that's not being reviewed through the communication. Yeah, but for those who see this before, maybe a bonus point is like the one even more surprising thing is like, now, if you slightly generalize equality to longer length to like n bits, yeah, you can still easily prove that deterministically you need like n bits of communication. But it turns out that if you have some shared randomness, which we will mention later, yeah, if you have some random coins shared between them, actually you can do much better. Yeah, so this is advanced comments. Yeah, if you are not familiar, it's totally fine. Yeah, but here so far just want to give you a feeling, yeah, of like a different computation model than Turing machine. Yeah, and yeah, I guess this is the time for quick questions. Maybe I'll check VLOGs. Oh, someone asked about classical content. Yes, content is also quite developed. Yeah. Mm-hmm. Okay, I think the question is fine. Okay, so maybe then let me move on. Okay, so now that we see some different computational models than Turing machine, let's also take a look at what kind of computational resource we can have. Yeah, so maybe the most intuitive one would be like time, like the amount of time you need to spend to solve a computational problem. But the nature, other computational resource could be also space, or like in a more technological language, it's like the amount of memory you need, yeah, to perform the computation. You can imagine if you have very, very limited space, yeah, you can even sometimes cannot store the whole input. Yeah. And there are also some slightly not direct intuitive computational resource. For example, something called nondeterminism. We will elaborate in a second. And randomness, which we mentioned earlier, or quantumness when people already ask, or interactions. This is also similar to like the communication we mentioned before. But I guess my point here is like there are so many different intuitive ways to formulate like extra computational resource you can use. And the beautiful things in theoretical computer science is like all these resources actually they can be quantified, meaning that they can be more mathematical study and even can compare with each other. So in the second half of the course, then this will be our focus. And this is in fact also the focus of the modern development of theoretical computer science. Yeah, but before delve into that, yeah, maybe let me still use some example to give you a feeling on what do I mean by different computational resources. So the first example is non-determinism. So at first glance, for people who haven't seen this before, this maybe sounds like a philosophical term or a physical term. Yeah, but what we really meant here is maybe referring to, for example, your experience of an aha moment, like when you are solving a math problem, you suddenly figure out how to do it, or when you're creating art, somehow you suddenly have a idea in your mind. Yeah, something like this. Yeah, but how to mathematically formulate this kind of aha moment in your experience or in the process of computation. So it turns out that in mathematics or in the theory of computation, people model non-determinism mathematically as something called verifiable guesses. Yeah, and mathematically, this is a little bit ugly to describe if you haven't seen this before. So let me use a very intuitive example. So this is a game maybe you played 20 years ago called Where's Wally? So the game is very simple. Yeah, there's a figure, yeah, on a very crowded beach or other places. Yeah, and the promise by the author is Wally is in part of is somewhere in this huge picture, but the goal is ask you to find it. Yeah, and can you easily find it for me? Yeah, maybe I'll give people 5 seconds if you can find it. Yeah, so you probably can already have a feeling that, oh, actually, it's not that easy to find it. Yeah, if I don't tell you where he is. But turns out that if I directly point out you, oh, this is where he is, it's very easy. Yeah, and this is exactly what do I mean by verifiable guesses. Yeah, it's like when people tell you or when you guess it, yeah, you suddenly have an intuition, he might be there. Yeah, and then you point out there, it will be very easy for you to verify. For example, if I mistakenly point out here to you, oh, what is here? It's also easy for you to verify, oh, I was incorrect. I was lying to you, or here, similarly. Yeah, so mathematically, actually just we model non-determinism as a verifiable guesses by writing this intuition down in the mathematical form. Yeah, sorry about that. And but indeed, there are actually also other nature problems beyond where's Wally, corresponding to non-determinism. And I guess it's also worth mentioning a little bit before we go into the next example. And this is also connected to the circuit model we talked about before. So this is called something called Boolean satisfiability problem. And there are several forms. Yeah, for example, the first possible situation is called circuit set. Yeah, the problem is that I give you a circuit and I ask you whether there's an assignment to the variables such that after you evaluate the circuits with these assignments, it evaluates to 1. Yeah, so maybe you can take a look at, there are 2 circuits here. Do you think they are satisfiable? Yeah, so it turns out that this one is not satisfiable, and it probably is not too difficult to see if you do some a check-in here. And turns out on the right, this circuit is satisfiable. Yeah, and this is easy to check because once I tell you what assignment make the circuit satisfiable, it's super easy. You just evaluate the circuit. But in the meantime, if you want to convince me it is not satisfiable, yeah, you probably need to enumerate all the inputs, something like this. So you can see that it is easy to certify, yeah, the answer is yes. And there's also other forms of a satisfiability problem when you write it as a disjunctive form, or sometimes people also call it a 3-set. Yeah, and similarly, this one is satisfiable by directly plugging in like a satisfying assignment, and the second one is not satisfiable. Yeah, so here, if you are not completely following, it's fine. Yeah, you can just think of it as, yeah, this is a canonical problem in computer science. Yeah, like kind of capture the non-determinism. Yeah, and I'll elaborate this in a moment. Yeah, and the point here is like non-determinism is referring to, yeah, you can, if you have a right answer, it will be very, very easy to verify it is a right answer. Okay, so I guess this is enough for the example of non-determinism. And the second example I want to talk about is randomness and quantumness. And for the quantumness, maybe I'll give more example and details in the future lecture. Yeah, so how can randomness really help in the computation? So maybe I want to use one of a simple, my favorite example called max cut. So we probably see max cut before in the previous lecture. The goal is to like find a partition for the vertices in a graph and maximize the number of edges crosses these two parts. Yeah, so in general, it's not so easy, yeah, to find the best cut. So sometimes people lower their standard. They just want to find as large a cut as possible. Yeah, and if you now have some randomness, meaning that you can randomly decide if you decide the way to cut it, actually there's a trivial algorithm as follow. Yeah, you just assign each vertex, yeah, to be on one side with equal probability. You assign it to be black with half probability, white with half probability. Yeah, something like this. And then you use it as a cut. And now if you do the analysis, you actually will realize that even this seems to be a super dumb algorithm. You just flip coins and decide a cut. But this cut already is pretty good. It actually already gives you the size of the cut is at least half of the optimal size on average. And how to see that? Yeah, you can see that for each edges, actually there are half probability being a cut edges, meaning that the two end vertices, they are assigning in different colors. Yeah, so I hope this roughly gives you a feeling that you are convinced that this simple random algorithm actually already doing an okay job. Yeah, but I also ask you like a food for thought question, maybe you can think offline. But okay, so now you told me you need randomness to do this, but is this randomness really necessary? Okay, and on the quantum side, maybe I'll give a classical example, but don't tell you any details. It's something called Shor's algorithm. Yeah, this algorithm, what we can do is that the input is some huge integer, and you can use the quantumness, yeah, to factor the integers very, very efficiently. And this is not known to be done, at least currently, not yet. Yeah, not known to be done efficiently without the help of quantum. Yeah, and similarly, a key question here is also like, can you remove the quantumness? Yeah, so I hope like through these examples of non-determinism and randomness and quantumness, yeah, you have a feeling of like, oh, computation is not just like Turing machine doing mechanical procedures. There are also much more ingredients you can add it and discuss, yeah, in this playground. Okay, so maybe now is also a good time for people to ask some question. Some, okay. Yes, someone asked about whether non-determinism and randomness are the same or different. Yes, indeed, they are actually different. Yeah, or I mean, yeah, formally people cannot prove they are the same or different, but we believe they are kind of different. Yeah, and I can delve into this more when we set up the problem even more properly, so that we can compare what do we mean by they are same and different. Okay, great. So now we have seen like different computational models and different computation resource, so we can kind of enter the modern study of computation, which I phrase it as a shift from computability to something called complexity. So what do I mean by complexity? It is very, very related to something called efficiency of computation. So as you see before, there are different computation models and different computational resource. But like according to Church-Turing thesis, everything can be simulated by a Turing machine. So why so interesting? Everything can still be done by mechanical procedure like Turing machine. But the point here is like, although Turing machine can indeed like simulate all these kind of different resources and models, but this kind of simulation could be very, very inefficient. Yeah, so imagine like you nondeterminism, although Turing machine can kind of simulate in some sense, but it will be intuitively very, very inefficient. And how can we formulate and formalize this kind of intuition that this simulation could be inefficient and study it? So this questions give birth to a field called computational complexity. And this is actually the home field of myself and the guest speaker, Li Jichen. And this is our favorite conference, Computational Complexity Conference. So basically a starting point is to take computational efficiency into account. And we want to study the amount of resource needed because as promised before, all of them can be quantified. And we use this amount of resource as to capture the complexity of a computational problem. And through like identifying the complexity and compare the complexity of different problems, and then the goal is to see if we can, through this lens, to understand different resources and different models better, rather than just reduce talk about everything through like Turing machine. Because as I said, although Turing machine indeed can do everything, but this is not so insightful. We want to have a more fine-grained understanding. But I talk so much about complexity, efficiency. What do I mathematically really mean? So now I want to give you a concrete formulation of computational complexity. And although we have so many different computational resources, here let me focus on time, which might be the most intuitive notion for people, and use an example to illustrate how we define it. So the example is to think about now the computational problem is to multiply two n-digit integers. So how can we model how difficult or like how much time we need to solve this abstract computational problem? So you will immediately there are some natural question you might ask about like when you're trying to formulate this mathematically. First, the algorithm designs matters. For computational problem, if you solve it with different algorithm, for example, if you use the school book multiplication, or if you use a definition of multiplication, it might be so slow. And in the meantime, Wikipedia also tell you that there are this fancy Harvard whole even algorithm can solve multiplication quite fast. So which one should we use? And it turns out that for our community, the consensus is to use the best possible algorithm. So when we talk about the complexity of a computational problem, what we always think in mind is what's the best possible people can do. But now then you can ask me, okay, what do you mean by best possible? When you have an algorithm, you still need to implement it, and the hardware and software implementation might matters. How can you decide what's best possible? So the community consensus now becomes like we use something called asymptotics, which I will elaborate a little bit later. But basically this is something like ignoring the difference between your hardware software implementation. And this will also be highly elaborated in the guest talk next hour. And finally, you might also ask, okay, so now we want to determine the complexity of multiplication, but for some input, like this input on the left, it could be super simple. I probably some people might already can tell me like what's the result by looking at it. But for some input, like something on the right, well, this also seems so scary. It might take me 5 minutes to solve it. Yeah. So when we talk about the complexity of a computational problem, what are we really talking about? And the consensus of the field is to talk about the worst case scenario. Yeah, we always focus on the worst possible inputs and how much time you need to spend on it. Yeah, so hope through this slides give you a little bit feeling on like when people trying to approach like defining something, yeah, mathematically, yeah, how they do it. Yeah. Okay, so once you have this kind of concepts, I can talk about like a core concept in the field of computational complexity, something known as complexity classes. Yeah, to formally define it is slightly involved. So here I decided to use a very informal definition, hope to convince you and give you the intuition on what does complexity classes mean. So a complexity classes basically is a collection of computational problems. Yeah, including, I mean, for example, multiplication problem could be one of them. And those computational problems should cost similar computational resources. And similar, I'll formally like argue it in the next slides. But maybe if we first stick to this informal definition, let's see what can we say about it. Yeah, for example, yeah, if we use our favorite computational resource time, then we can define this complexity class called P, which is defined as the collection of computational problems that don't cost too much time. And here I intended to use a vague term, don't cost too much time, and I'll explain what do I mean next slides. But if we move on, we can also define a class called NP, which is basically P, the original complexity class, plus non-determinism, like plus you can have verifiable guesses. And we can also define BPP and BQP as like the complexity class P plus like randomness and quantumness, and so on. Like we can define P space, which is problem that doesn't cost too much space. Okay, so probably now I believe some of you might already got overwhelmed by me, and you might think, okay, yeah, why should I care? Yeah, this complexity classes seems like a puzzle. Like there are so many notations, it looks so complicated. But maybe one motivation for you is like, well, actually, this is quite important. Many people care about it. Yeah, although to explain how it is important is difficult, but the money speaks. Yeah, at least like resolving one of the central questions in complexity theory, the P versus NP problem, will give you $1 million. Yeah, so hope this wake you up. Yeah, and make you ready to bear with me for a few more slides. Yeah, but in short, yeah, complexity classes here just an attempt to put computational problems with similar like a cost in terms of computational resource together, so that we don't study single computational problems like one by one, we study them collectively. Okay, so now maybe, yeah, after convince you the importance of complexity classes, I probably have to say a few words on what do I mean by like cost similar computational resource and does not cost too much. Yeah, so when I say similar, actually similar in the asymptotic sense. Yeah, in the sense that now rather than focus on like a specific problem, we think of a problem as a family of problems on different input size. And we consider like for each input size, how much like a resource it costs. And we want to look at the scaling of the amount of resource needed by this computational problem. So this is something called asymptotic. And we also use this something called big O notation to ignore the minor factor or constant not scale with the instance input size, so that we can put different computational problem into the same complexity class. For example, like this if the scaling of the time complexity of problem is something like this, 2n squared plus 100, to a complexity series, they just think of it as n squared. Yeah, and similarly, if it looks like this scary things, to a complexity series is just like a 2 to the n. Yeah, so you can see that this help simplify a lot and also can help you put lots of different things together in the same bucket and to argue and analyze about it. And finally, about the not cost too much. Yeah, here the community consensus is talking about polynomial time, meaning that the scaling is a polynomial, which I'll explain in the next slides, as well as Li Jie will talk about this in his guest talk. Yeah, so to give you an example on like the concrete mathematical formulation of complexity classes, yeah, let's consider this two scaling, yeah, of say the time complexity of two different computational problems. So F is something like when the input size is 2, is cost you 20 seconds. Yeah, and G is something like when the input size is 10, it costs you 2 to the 10 over 10. It's like just 2 seconds. So you probably can see that if n is quite small, okay, so actually the first one, the blue one, the F actually costs much more time. But when you make the input much larger, in the end, actually the orange one, the second input, the second scaling, the second function G, surpasses the first one. And this is just an example to illustrate to you that in complexity theory, in mathematics, we actually focus on the rightmost regime. We want to care about the long-term scaling of a problem, yeah, and use this to determine whether a computational problem is efficient or not. And this further tells us which complexity classes a computational problem should lie in. Okay. And in Li Jie's guest talk, he will give a philosophical justification of why this makes sense. So finally, yeah, having this kind of complexity classes set up, yeah, people can discuss lots of things. Yeah, and mainly what people do now becomes like rather than comparing different computational problems, now we compare different complexity classes. Yeah, for example, now P, you can think of basically as a collection of computational problems that can be solved in polynomial time, meaning that it can be solved efficiently by some Turing machine or an algorithm. Yeah, and NP now becomes just a collection of problems that can be solved efficiently with the help of verifiable guess. Yeah, so given this, yeah, then the P versus NP problem basically is a synonym of asking whether non-determinism can help you, whether non-determinism can like help you speed up the computational time much faster. And similarly, the P versus BPP, P versus BQP problem is then asking whether randomness and quantumness help. Yeah, so I hope, yeah, through the discussion of complexity classes at all, yeah, can give you a sense of like what's the modern development of the theoretical CS is focusing on. Yeah, we instead of study specific problems, we look at a collection of problems called complexity classes and study their relations. Okay, and yeah, I guess now is a good time for post for questions. Yeah, and let me see if there's immediate important questions. And you can also vote the questions so that I can see the one people are interested in the most. And in the meantime, I know some of you are like complexity theorists or theoretical CS before. I also encourage you to think about these questions like, okay, now how would you explain P versus NP to your friends? Yeah. For example, yeah, last semester I am like TF in a course called Science and Cooking. Yeah, and in the first TF meeting, the other teaching fellows, they are from all different departments, like chemistry departments. They ask me, oh, what are you doing? Yeah, and then I'm saying, okay, my lifelong goal is to solve P versus NP problem. Have you heard of it? And everyone say yes, but they don't understand what it is. And the example I gave them is the following. Basically, P versus NP is asking you that even if you can test whether some food is very good, it doesn't mean that you can produce a good recipe very, very efficient. Yeah. So the first one about whether you can tasting something good is something like, oh, this is very valuable guesses. Like when some people give you something, some food, it's easy for you to tell whether it is delicious or not. But that not necessarily means that you can produce like a good food. So this is some informal but illustrative and fun way to explain P versus NP to your friend. And I encourage you to think about your own example. Great. So yeah, so given a time limit, maybe, yeah, and I also didn't see in urgent questions. So let me conclude this lecture with something very, very important in theoretical CS, the gen of theoretical CS, something called reductions. Yeah, so previously we were talking about complexity classes, and the big picture is that, oh, now we have so many different classes. We have P versus NP, and we want to attack them. We want to understand their relation. But what kind of tool can we use? And it turns out that this thing's called reduction is the main sword in the theory of computation for people to study like either complexity classes, their relation, or beyond. And informally, what reduction really means actually is quite simple. It's just the following. Suppose, let's say, yeah, you have two computational problems, A and B. Yeah, we say A can be reduced to B if A can be efficiently computed with the help of B. Yeah, so you can, so mathematically, yeah, we use this notation, A less than or equal to B. You can just think of, oh, so because if I can solve B, then A necessarily being solved by me. So that's why it looks like this. And let me give you a few examples to enhance this feeling. Yeah, for example, A can be multiplications. You want to multiply something. And B can be addition. Okay, you might think that's weird, why addition? But it also makes sense because multiplication in hindsight actually just like adding something for many, many times. So indeed, with the help of addition, you can solve multiplication kind of efficiently, although this is not the best way to do it. And the second example actually is from like the previous lecture. Yeah, basically the church Turing thesis is a hypothesis that actually you can reduce all the plausible computation. Maybe feasible might confuse some people, but it's like all the possible computation, you can reduce it to Turing machine. Namely, yeah, if with the help of a Turing machine, you can solve any computational problem. Yeah. And finally, maybe also as a joke example, yeah, you can also think in your life, like for example, for a kid, he or she can do nothing. So everything he needs his parents, yeah, to help him do anything. He can reduce everything to his parents, his or her parents to do anything. Yeah, but I'm not aware of any mathematical proof for this one. So if you know it, you can tell me. Okay, so yeah, so now we have the intuitive, informal definition of reductions. Now I want to convince you that it is indeed powerful and ubiquitous in the study of computation. Yeah, and first, I want to talk about different ways to think about reductions. Previously, we say by definition, maybe it's not so intuitive, but the first intuitive way to think about is like thinking of reduction as like a black box, or technically it's called oracle. In the sense that you can think of A, the computational problem A, think of B as a black box he can use. So you can either plug in A or B with one of the example you see previously. Yeah, a kid can use the parents as a black box and keep querying it, asking questions. And similarly, you can also think of B as a subroutine or a macro. If you do programming, this might ring some bells. Yeah, it's like you can use lots of macros and subroutines. Yeah, and collaboratively, they might help you solve your original problem. And mathematically, there's also like two main different forms. Yeah, which maybe I won't elaborate too much. But the first one is just that you can turn the input of one problem into the form of the input of the other problem. Like you turn circuit set problem to a three set problem. Or you can do something like known as Turing reduction, which is basically the Oracle model. Like you can keep thinking of B as a black box you can query to, and you ignore the resource used by this black box. Okay, so here, this slide just want to give you a sense that reduction is not just what I described, that the basic simple definition actually is quite rich. There are multiple ways to think about it. And now I'm going to give you two examples to illustrate the power of reduction. And both examples are in a serial computation. So this probably is the most technical part of the lecture. So feel free, yeah, to like just watch it as a movie. And if you are interested in the detail, you can talk to me offline. So the first one is the Cook-Levin theorem. So this is saying that for every problem in NP, yeah, can be reduced to three sets in polynomial time. Yeah, and NP, just to record, is this collection of computational problems that can be solved efficiently with a verifiable guess. Yeah, and technically people then call this three set, it is NP hard, because it's like every problem can be solved with the help of three set. So three set is like quite hard, it's at least as hard as like NP problem. And the Cook-Levin theorem, in hindsight, its proof basically is using reduction. Yeah, the idea is like, okay, so now you have an NP problem, which has a form of like, you can be efficiently verify if the guess is correct or not. Yeah, the idea is just use the circuits to help you do this verification. And then you further reduce circuit set to three sets by like locally dissect these circuits. Okay, the detail is not important. Yeah, I'll just use a simple example to illustrate this. And let's go back to our favorite, where's Wally? Yeah, for example, this is a NP problem because you can easily verify whether Wally is here. Yeah, and it turns out that you can just put in so many circuits locally, help you brute force, yeah, kind of. Yeah, and figure out whether Wally is there. Yeah, and this is exactly a circuit set problem. And finally, you use some mathematical tricks, you can simplify the circuits into three sets. Yeah, so in hindsight, this is Cook-Levin theory. But I also hope what you feel is about the reduction. Yeah, it's like in the beginning, we want to solve the where's Wally problem. But this Cook-Levin theorem tell you that actually, if you know how to solve the three set problem, the Boolean satisfiability problem, then actually you can solve the where's Wally. And in general, you can solve any problem in NP. So this is like a reduction. Yeah, and yeah, I know I skipped lots of details here. I'll talk a little bit more, yeah, in the future lectures. Yes, and due to time limit, this example, unfortunately, maybe I have to talk even faster, although this is super fascinating. Even I think maybe it might be new even to some CS people. Yeah, but let's go back to our communication complexity game example. Yeah, and in this communication game, the problem is the following. Yeah, Alice and Bob both receive like two graphs. Yeah, we see this graph before. And the goal is to see, and the promise to you is that Alice receive a graph that is three colorable, in the sense we talked last time. Well, Bob's graph actually is not three colorable. Yeah. So if you know that one is recolorable, you can use 3 colors to color it, and the other is not, that means that there definitely exists an edge, yeah, that not belong, just belong to exactly one side. Yeah, sorry. So the goal is to find at least one edge, yeah, that is not belong to both sides. Yeah, this is the communication goal. So this is also very similar to equality. You can feel that because we know that the input are not equal, but now just the goal is that I want to figure out what edge they are different. And the beautiful thing here is that actually, although this is a communication game, this actually can be reduced to some property of Boolean circuits in the following beautiful way. Yeah. So suppose you have a Boolean circuits for like solving this recoloring, in a sense that the input is the edges of graph, and the output will tell you 0 or 1 according to whether this is colorable. Yeah, if you have this kind of circuits, then you can solve this communication game in the following way. Yeah, so for example, yeah, like this is the input of Alice, this is the input of Bob. Yeah, we know that they differ by an age, meaning that in this age, Alice have an age, so it is 1. Bob doesn't have age, so it is 0. So Alice and Bob in a communication game basically want to identify this age. And what they can do in a communication game actually is exactly using these circuits to help them communicate. So you can imagine in the beginning, they are on the top. Yeah, I at least know that her output will be 1 because it is colorable, and Bob knows it's 0 because it's not. And because when you encounter AND gate, Alice know both of the input to AND gate is 1, but Bob know that one of them should be 0. So Bob will tell Alice, okay, let's go left. We go to this side to make sure our inputs still disagree. And for the next level, yeah, if it is OR, Alice know that how to keep their input being different. So let's go left again, and so on, go right. And in the end, this can guarantee you to end with some places where their input are disagree. Yeah, it's not exactly 1, 0. So I hope, yeah, this roughly gives you a feeling that, yeah, if you can have a circuit to solve the 3 coloring, then you actually have a communication protocol. You can solve a communication game. So this might be a little bit fancy, but as I always emphasize, this just want to give you a feeling on the power of reduction. So let me end with a slightly lightweight example to wake people up. Yeah, like to convince you more on why reduction are ubiquitous. So for example, in cryptography, what people did is like they reduced factoring problem to some crypto system in a way that, oh, so if people can break it, that means that you can factor the problem. So this is another application of reductions. Or like in real life, there's also reduction. For example, in this mini course, basically you can reduce me to all the guest speakers. They are like helping, and maybe also all the teaching staff. Yeah, like basically it's like all of them like help me to organize this mini course. Yes. So yeah, so this is reduction, and I know this is a huge topic. So if you are interested in this and have more questions, yeah, feel free to ask later. Yeah, and also given a time limit, maybe I'll skip the Q&A now. Yeah, and quickly tell you what's going to happen next. Yeah, so actually in 4 minutes, yeah, Li Jie is going to talk about the philosophical foundations of complexity theory. Yeah, and you probably all received his abstract in the morning email. And later, like 3 hours later, Rayo is also going to talk about like how to use uncomputability theory to prove Gödel incompleteness theory. And Prahlad is going to talk about 4-color theory tomorrow morning. And we also have a philosophical lecture next Monday. And tomorrow we will then start to talk about things in the biology and physics module, which will be quite different from today, but should be very fun. Okay, so yeah, so in summary, today we talk about different computational models, different computational resource, and this motivated us to define complexity classes, which put problems with similar cost of resource together. And in the end, we talk about reduction as a powerful tools to understand the relation between computational problems and complexity classes. Okay. So yeah, maybe to give people some time to rest before Lee just talk, I think I'll end up with this food for thought and exercise slides, yeah, for you to glance at. And yeah, thank you all for your attention, and see you in Lee just talk.